Hi there, my name is Karina Abraham. I am a senior studying aerospace engineering at Purdue University, and today I will be teaching you about rocket science. More specifically, I'm going to give you a tutorial on the basics of orbital mechanics. So hopefully by the end of this, you will understand these things a little more, but also be able to plan your own mission. So say that you live on a planet called Earth and you want to visit your friend who lives on Mars. So what would you do? Well, there's a variety of ways to get there, but not all of these ways are made equal. There are some that will burn a whole lot of fuel, and there's others that will take a whole lot of time to get to your destination, so you want to be smart with the method that you choose. So one of the methods that is used all the time is something called a Hohmann transfer, which you can see in the blue dotted line right here. So this is what we are going to be focusing on today. But before we get into Hohmann transfers, we must discuss the vis-viva equation. So this says that v, or the velocity of the orbiting object, is equal to the square root of gm times 2 over r minus 1 over a. So g is our gravitational constant, m is the mass of the central body, r is the distance between the orbiting object and the central body, and a is the length of the semi-major axis. So this equation is super important for our calculations for Hohmann transfers, as you can see in the upcoming slides. As for how you do a Hohmann transfer, what you will do is when you're at this certain position in your orbit, you will fire your thrusters, otherwise known as a burn, to exit your current orbit and enter this blue Hohmann transfer orbit. Then you will cruise for a little while until you get to Mars, at which point you will fire your thrusters one more time and enter Mars orbit. We must also discuss delta V. So delta V is the amount of energy that you need to perform a maneuver. So the less delta V required, the better. So what I mean by that is, say you're here on Earth, you are currently traveling at a velocity of VI. But if you want to exit this orbit that you're in right now and enter a new orbit, you need to get to a velocity of VF. So the difference between these two is our delta V, and this can tell you the amount of energy that you need to do this. So now here comes the fun part. Let's do some math. So you will recall from an earlier slide that V is equal to the square root of gm times 2 over r minus 1 over a. So you will use this equation to calculate your initial velocity and your final velocity as well. You will also recall that delta V is equal to VF minus VI. So after you do all of this, you will get these two equations. So delta V1 is the delta V that you need for this maneuver, and delta V2 is the delta V that you need for this maneuver. So at this point, you can just plug and chug. The Earth and Mars orbit radii can be found here, and your delta V1 will be 2.94 kilometers per second, and your delta V2 will be 2.65 kilometers per second. So in total, when you add these two values together, you will get a total delta V for your mission of 5.60 kilometers per second. So this value is super important when it comes down to planning your missions, because the more delta V that's required for a mission, the more propellant that you will need, for example. And if you need more propellant, that means you need to deal with other things like structural requirements and other things like that, which can bring up a whole other host of issues. But that's an issue for another day. So Hohmann transfers are something that we use all the time in our missions. You can see it actually being used here for the InSight mission. It was launched from Earth in 2018 and it landed on Mars 6 months later. So hopefully this helps you in your future travels. Bon voyage!